Cayley table for quasi groups?
Yes. Yes. So a Latin square is more specific than a Cayley table. A Cayley table just has to have all of the elements inside of here, and then the Latin square has the extra requirement of each element appearing once in each row and each element appearing once in each column. So you've got this extra requirement. Yes.
Okay, thanks.
Yes. Okay, I promise there are non-associative triples in here. I just did a bad job of hitting them. They exist, I promise. All right. You might not have an identity element. So there might not be an identity element here. There might not be inverses, and it's not required to be commutative either. So not every quasi group is a group, and there really, really are, I'm discouraged, but I promise there are non-associative triples in here. Okay, so now playing with these things called quasi groups, we can create a new message authentication code. Everything you've seen before is totally basic first semester, second semester, abstract algebra graduate level. Very basic, nothing new going on here. What we're gonna start now is my research. So this is the place where I came up with a new message authentication code, cleverly entitled QMAC, because we're working with quasi groups. You gotta have a cool name. So here's how it works. The message is going to somehow or other, and this is, again, you've got to remember, I am a theoretical cryptographer. I don't care how this gets implemented. Somehow or other, the message is going to get translated into elements of a quasi group. Somehow or other. I don't care. Somebody else can figure this out. This is not a big deal. The secret key for my message authentication code is a way of inserting parentheses, okay? So if your message, for example, looks like M1, M2, M3, M4. So let's say that my message is M1, M2, M3, M4. One possible key could be M1 circle M2, and then that circle M3 circle M4. A way of inserting parentheses. That could be one possible key. Another possible key could be M1 circle M2 circle M3 circle M4. Okay, so those are potential different keys. How are you going to insert parentheses into your message in order to do your computations in the quasi group? And then your authentication tag is going to be the result of whatever that set of parentheses was multiplying out. So you're going to multiply all of those computations together using the way that you describe the parentheses, and that is going to be your authentication tag. Almost. I'll tell you almost in just a second. But the story of where this came from is actually kind of funny. So usually what happens when you're in grad school is your advisor gives you some papers to read and says, you know, here's a place to start. Here's research that's been done in this area. See what you might be interested in. Is there any idea that you could have or open questions in here that maybe you could look at or stuff like that? All right, so what he did, I got a paper to read, and there was a description of a message authentication code using quasi groups, and then there was a statement about how many keys there were, like the total number of keys. And I read it and I'm like, that's not right. And I thought about it, and I thought about it some more, and I thought about it for 2 days. I'm like, that is not right. That is not the right number of keys. That is wrong. And clearly I'm missing something because this paper is peer reviewed and I'm a second-year grad student, and clearly the peer reviewers are right and I'm not. And what I finally figured out is what was wrong. I was misunderstanding their protocol, and therefore I was counting the number of keys according to what I thought their protocol was. And I turned their protocol into QMAC, the one that I thought. So what I misread the paper as ended up as my doctoral dissertation. Sometimes if you misread something and are being stupid, you can get a PhD out of it, basically, is the moral of the story here. All right, so that's my read things carefully, but not too carefully, because maybe you'll get an additional idea. All right, authentication tag, almost. We want to replace every innermost product M sub I circle M sub I plus 1 with M sub I circle C and then circle M sub I plus 1. So if my key, and C is a element from the quasi group. So if my key was M1 circle M2, circle M3, circle M4, instead, what I'm gonna do is M1 circle C, circle M2, and then M3 circle C, circle M4. So it adds an extra layer of what looks like ridiculousness at this point in time, but we'll talk about why that's actually important when we talk about the security in a little bit, okay? So you've got this extra secret element of your quasi-group C, and you're replacing all of the innermost multiplications here. All right. Notice, this is important. The security of QMAC depends on how non-associative your quasi-group is. If your quasi-group is associative, that means you can move the parentheses and nothing changes, then every single key, every single parenthesis scheme will give you the same authentication tag. That is a really bad message authentication code. I'm just saying, it's really easy to forge. If you have what I'm calling a highly non-associative quasi-group, then if you move your parentheses around, you will get different authentication tags. And that is what we are looking to do. We would like to have different authentication tags. So as long as you have what's called a highly non-associative quasi-group, you will get different message authentication tags. That doesn't necessarily mean that QMAC is secure, but it does mean that we're going to get different message authentication tags out. Okay, I've been talking a lot. Questions before we look at public and private information in an example? John, yes.
With that paper you read, did you think that it had more possible keys or less than it described?
Well, that's a good question. I think more, but I'm not positive. I think more, yeah. But wrong, we're just saying wrong. I was wrong.
It's a good way to be wrong, though.
It is a good way to be wrong. It's a good thing to get a PhD out of being wrong, yes. Anybody else? Other questions before we keep going? Okay, public-private information. Oh, John, one more time.
Yeah, so with your C there, if you did have a group that was associative, you still have like a little bit of security, would you say, with C?
Yes, a little bit. Not nearly enough to stand against a brute force attack. So you still want a highly non-associative quasi-group. When I first did this, and I'll talk about why that C is in there if we have time at the end of class. When I first did this, I didn't have the C in there. And I started writing up a bunch of stuff, and my advisor found a problem. Whether or not it's actually a problem is debatable, but according to the definition of quasi-groups, it is in fact a problem, or according to the definition of message authentication codes, it is in fact a problem. So we inserted the C to fix it. So the C is not really exactly there for adding a lot of security. It's just intended to fix a technical problem with the definition. And I'll get there at the end, assuming that we have time. Okay. Public-private information. So the public information is the quasi-group itself, your Latin square, basically. The message, remember we're doing encryption separately from all of this, right? So we're assuming the message is public. And Kirchhoff's principle, the method for computing the authentication tag is public. Very important, Kirchhoff's principle. The only private information is the parenthesis scheme, and I'm including that secret element C along with the parenthesis scheme. So you can kind of say parenthesis scheme plus that secret element C, both of those. All right, let's do an example. Let's see how this works. Let's do an example, and then we'll talk about security. So same quasi-group that I was using before. same quasi group. Let's say that we have a message 146277. So the N is equal to 6 in this case. I'm blocking my message up into 6 characters, 146277. And then there's my parenthesis scheme right there. I am not going to attempt to read you my parenthesis scheme. It is not going to work, not going to happen. My constant is C equals 3. So I'm going to have you do this, but I'll put it down here. Here's my authentication tag. That's an innermost multiplication. So I need to replace the M1 circle M2 with that M1 circle C and then circle M2. That's an innermost multiplication right there. So I have to replace that one. And then there's another innermost multiplication, M3 circle M4. There's another innermost multiplication there. So I got to replace that one with M3 circle C circle M4. Okay, I got to replace that one. And then we've got the last two, circle M5, circle M6. So take a minute. Let's see if you can do the authentication tag. Remember, across the top is the first element. Down the side is the second element. Take a minute, work this out, grab a piece of paper, some scrap paper, something like that. Across the top is the first element, down the side is the second. See if you can come up with the message authentication tag for this key. So do the inside ones first and then keep going. Anybody want to try and answer with fingers, or we're still working? Do we want to try and answer with fingers? Laura's got a 7. We can do comments also. I can't read that, John. 7, probably. 7, thank you. I'm now doubting myself because I have 4 and I'm not convinced that's right. We're getting a bunch of 7s. We might need to write this out. Let's go ahead and do a whiteboard instead and write this out here.
I also wasn't convinced, but Laura's pretty trustworthy. So.
Oh, okay. Well, mine says 4, but I'm not convinced that's right. So let's double check this one here. All right, I've got this in front of me. Here we go. Okay, so we want to do 1 circle 3, circle 4, and then we want to do circle, there are 4 parentheses there. There's a lot of parentheses there. 6 circle 3, circle 2, circle 7, and then circle 7. Okay, so 1 circle 3 should end up being 5. Are we good with that? 5 circle 4. I wonder if I reversed you and put top inside. That might have been what happened. I might have reversed these. Okay, 6 circle 3 should be a 2. We're good with 6 circle 3 being 2. I'm getting nods. Okay, so 2 circle 2, circle 7, and then again circle 7. I think I probably reversed them. 5 circle 4 is a 7. We like that. 5 circle 4 is a 7. 2 circle 2 is a 7. So we've got lots of 7s in here. And then let's see, 7 circle 7 is 0. So we've got 0 circle 7. 0 circle 7 is 1. So 7, circle 1, and that's going to be 7. I am pretty sure that my example had across the top second and down the side first. So that's what's going on here. It's been a while since I presented this. We are good with 7 the way I described it. If you do across the top second and down the side first, then you will get the answer that is on my slides, which is 4. So that is, I believe, what is going on here. Okay, so there we go. Go back to slides. We're good here. And that's what she sends, either 7 or 4, depending on how you talk about your order of operation. All right, changing K will probably change T. If I had more time, if you were in class, I would make you do this as well. Here's another example. You can come up with another constant, another QMAC key, and if you do side and then top, you'll get 6. So changing the key is probably going to change the authentication tag. That's good. We want something like that. We want something that if you change the key, you are also going to change the authentication tag. That's helpful. All right, couple of things to talk about. First of all, we'll get a little practical. My advisor made me get a little practical, not a lot, but a little. So how are you going to exchange this private information, right? How are you going to represent the key? It is not practical, not feasible for Alice and Bob to send a parenthesis scheme back and forth, especially because we're going to need to talk about size at the end of this, how big these quasi-groups have to be, how many keys we possibly need to get some security, and they're going to be long. So it's not feasible to exchange a parenthesis scheme. What we're going to do, and this is also part of my research, and it was kind of a cool idea, if I do say so myself, that I came up with when my advisor said, well, you have to figure out how to exchange this key. I'm like, I'm a theoretical cryptographer. I don't really care. And he's like, you have to figure out how to exchange this key. Fine. All right, what we're going to do is represent this as a string of integers followed by the constant. And the integers are going to represent the order that you're doing the multiplications. What order are you doing the multiplications in? So here's an example. Let's go back to that first one that we had. So we have 5 different multiplications that are happening here, right? 5 different multiplications, circles, etc. Okay, and I've also got a constant going on here. Fingers. Which multiplication am I doing first? There are multiple right answers. Or if you don't have video, but I would like you to participate in the comments, give me a number. Which multiplication is being done first? There are multiple correct answers. I'm getting some comments via chat here. What else do we got? We've got 1s, we've got 3s. Yes, either of those is going to be a correct answer. So you could say you're doing 1 first, or you could say you're doing 3 first. So here is a possible QMAC key. Remember, we're going to take that secret element and just throw it on at the end. 1, 3, 4, 5, 2, and then that constant. That one works, right? 1, 3, 4, 5, 2, and then that constant, that's going to work. Or I could switch the 1 and the 3 around because we both said that you can do either of those first. 3, 1, 4, 5, 2. Are there others? Other possible keys. Sarah's saying, yes, I can see you nodding. Therefore, Sarah, turn audio, unmute yourself, and give me another one. This is what happens when you nod, and I can see you. What's the other one?
You can do 3, 4, 5, 1, and then 2.
3, 4, 5, 1, 2. Yes, that is not my next one. That's my last one, but you can totally do that. 3, 4, 5, 1, 2. You could also do 3, 4, 1, 5, 2, and there are probably others as well. So a bunch of different keys. John, question.
Would I be right in saying that 1 can kind of be moved around anywhere as long as it precedes 2?
Yeah, as long as 1 precedes 2, you can move 1 around pretty much anywhere. So this is definitely not, I don't think, an exhaustive list. I don't believe that this is an exhaustive list. You could probably do 1, 3, 4, 5, 2. That would be another one. Oh no, that's on here. Maybe this is an exhaustive list. I'm just looking. 1, 3, 4, 5. This might be an exhaustive list at this point in time. Not positive. Okay, so if you're talking about the size of the key space, this makes life a little more complicated. because we can't just say n factorial for the number of keys, right? All of these keys, they're different if you look at the order that the multiplications, the order that the numbers appear, but they're the same key. They all represent the same key. So we can't just say n factorial because we'll be overcounting. In addition, there are probably some strings of integers that you can come up with that do not represent a legal multiplication scheme. And if you played with those, there are definitely some that you could come up with that do not represent a legal way of multiplying things together. So our key space is not as big as n factorial, and that's sad, because even if you are a theoretical cryptographer, it's still very important to know how big your key space is to decide if this is possibly, maybe, secure enough to earn your PhD or not. Not positive. We got to have a big enough key space. That's the next thing